Hello everyone and welcome. We are Applied Artificial Intelligence Group 2 and we are excited to present our project on predicting customer churn in the telecom industry. I am Zoher Sabunwala and I have my awesome team Jasmeet Kaur and Jagadeesh Kumar Sellapan with me. In today's competitive telecom market, understanding and mitigating customer churn is crucial for business success. Churn, simply put, is when customer cancel their subscription or stop using a service. For telecom providers, this directly translates to lost revenue and diminished market share. Research shows that retaining customer is significantly cheaper than acquiring new ones. For instance, SAM found that improving churn prediction accuracy enables better targeting and retention, especially in saturated markets. Acquiring new customers is far more expensive than retaining existing ones. Therefore, accurately predicting which customers are likely to churn is vital. This allows business to proactively implement targeted retention strategies, offering personalized incentives or addressing customer pain points before they decide to leave. In another study, WAG demonstrated that machine learning models like random forest can achieve up to 99% accuracy in telecom churn prediction, proving that the problem is highly solvable, but only with the right approach and data. But simply predicting who will churn isn't enough. We need to understand the value of the customers we are trying to retain. This is where customer lifetime value or CLV comes in. CLV is a metric that predicts the total revenue a business expects from a single customer over the entire relationship. Building on the work of Galdis, we recognize that integrating customer lifetime value into churn prediction models enables businesses to focus their retention strategies on customers who offer the greatest long-term value. Furthermore, Wang emphasized that combining churn and CLV prediction allows telecom providers to rank customers not just by their risk of leaving, but also by their overall importance to the company. This integrated approach helps us to prioritize our retention efforts, focusing on high-value customers who contribute the most to the bottom line. Traditional churn prediction models often rely on simple metrics like how long a customer has been subscribed or how frequently they use the service. These methods are limited and don't account for the dynamic nature of customer behavior. Our approach is different. We have developed a two-stage machine learning framework. In the first stage, we build a regression model to predict customer lifetime value CLV for each customer using behavioral and demographic features. This is especially useful in cases where actual CLV data is missing or hard to compute in real time. Then, in the second stage, we use the predicted CLV along with the other customer attributes as inputs to the classification model that predicts whether a customer is likely to churn. Then, in the second stage, we use the predicted CLV along with the other customer attributes as inputs to a classification model that predicts whether a customer is likely to churn. This approach allows us to go beyond traditional churn prediction by prioritizing high-value customers who are at risk of leaving and enabling businesses to act earlier even before complete revenue history is available. Our framework draws on the idea introduced by Galdis and expanded by Wang that combining CLV with churn predictions help in making smarter, value-focused retention decisions. Moving on to next slide. As you can see in this flowchart, in stage 1, we use regression models like linear regression, polynomial regression, decision trees, and random forests to predict each customer's lifetime value based on behavior and demographic data. Then in stage 2, we use predicted CLV as an input feature in our classification models. Moving on to the next slide, let's take a closer look at the dataset used in our project. We started with a telecom dataset of 3,150 customers, each described by a mix of behavioral, demographic, and subscription-based features. As part of data cleaning, we removed duplicate records and standardized column names and formats. This left us with only 2,850 rows. During exploratory data analysis, we further refined the data set. We removed customers who had zero values for both call duration and SMS frequency, essentially inactive users. These users add noise and can distort model performance. After this filtering, our final dataset consisted of 2,765 valid customer records. One of the key challenges we noticed was class imbalance, which we'll cover in a minute. While exploring the data, we found that customer value feature was highly right skewed, which is common for financial metrics. To address this, we applied a logarithmic transformation which helped to normalize the distribution and improve model performance in the regression stage. As we mentioned earlier, a major observation was the class imbalance in the target variable. Only about 15% of customers were labeled as churn. To address this, we use SMOT, a popular oversampling technique that generates synthetic minority class examples. Importantly, we applied SMOT only within the training fold during cross-validation to avoid data leakage. We conducted a thorough univariate analysis to understand the distribution of each feature. This involved plotting histogram to visualize frequencies, central tendencies, and potential outliers. For example, we found most of our user base as young adult concentrated around 20 to 30 years of age. In our bivariate analysis, we use scatter plots to examine the relationships between pair of numerical variables and identify correlations. As you might expect, we saw a strong correlation between second of use and customer value. This kind of visual exploration provided early insight into the drivers of CLV and churn, helping guide both feature selection and model design. After data cleaning and EDA, we moved on to feature selection to determine which variables were most useful for our models. Our goal was to retain features that were predictive, had low multi-collinearity, and carried meaningful signal for either customer lifetime value or churn. For regression stage, focused on predicting CLV, we dropped features like subscription length, which showed redundancy and low correlation with monetary value. However, for the classification stage, predicting churn, we retained subscription length because it showed a clearer relationship with customer retention. You can see in the bar chart the features selected for both stages. Features like frequency of SMS, second of use, and distinct call numbers were strong behavioral indicators and were used across both stages. Categorical features like tariff plan, status, and complaints also contributed significantly, especially for churn classification due to their strong separation power between churn and non-churn user. We also retained features like call failure and age group, which contributed moderate but meaningful signals to both stages. The final dataset we used for modeling included second of use and frequency of SMS, capturing customer engagement, charge amount, tariff plan, and status reflecting account types and subscription models, and engineered features, customer value, which we first predicted in the regression phase and then used as an input to our churn classification model. Together, these features enabled us to build a robust and interpretable two-stage pipeline capable of not only predicting churn but also prioritizing high-value customers for retention efforts. Thank you. Over to you, Jagdeesh.
Thank you, Zoher, for the excellent presentation so far. Now that we've established the importance of CLV in our problem statement, let's dive into our next technical step, building a robust model to predict CLV for each customer. This predicted CLV plays a crucial role in our second stage, enabling us to prioritize retention efforts effectively, particularly in situations where real-time revenue data isn't readily available. Our goal was to find the most accurate and stable regression model. We evaluated several as summarized on the slide. Our baseline model was linear regression, which achieved an R squared of about 0.87. While this was a decent starting point, the model struggled to capture the nonlinear patterns that are typical in customer behavior data. Building on this foundation, we implemented polynomial features. This allows the model to capture more complex curves and interactions. The impact was significant. Our cross-validated R squared jumped to around 0.96. Through cross-validation, we confirmed the model's performance wasn't just overfitting, but represented genuine improvement in its ability to generalize new data. We explored degree 3 polynomial features as well, but found that degree 2 provided the best balance of complexity and performance, as higher degrees become more sensitive to outliers without meaningful accuracy gains. Next, we explored tree-based approaches. A single decision tree regressor showed promising initial results with high R squared of 0.99 on the training data. However, when we tested it through cross-validation, the model revealed instability. Both the R squared values and the error rates fluctuated significantly across different data folds, suggesting the model was overfitting, a common limitation of individual decision trees. This naturally led us to random forest. Random forest combines hundreds of decision trees, each trained on different samples of data, and averages their predictions to make more stable and accurate estimate. This technique dramatically increases stability and reliability. As the results show, random forest emerged as the top performer. It achieved the highest R squared at 0.995, explaining nearly all the variance in CLV. More importantly, its root mean squared error was extremely low and stable during cross-validation, averaging just 0.08. The low and stable RMSE demonstrates that our predictions consistently stay close to the actual values across different customer segments, reinforcing our confidence in the model stability. So, the performance numbers look great, especially for random forest. But we also wanted to visually check how well these models are performing across the board. That's where these residual plots come in. They basically show us the prediction errors for each customer. Let's look at the polynomial model first on the left. What we are looking for is a nice random scatter of dots around zero line. And mostly, it looks pretty good. Most errors are small within that plus or minus 0.5 range. There may be slow curve down low, likely due to a few unusual customer data points, but nothing too alarming. The spread of errors is fairly consistent too, which is good. It tells us that polynomial approach did a decent job capturing the general trends. Now look at the random forest plot on the right. You can immediately see it's even better. The errors are much more tightly around zero. That tells us that predictions are generally more accurate. And crucially, how the spread of these dots stays really consistent from left to right. And it's a sign of really a stable and reliable model. While we slightly more variability in predictions for lowest value of customers, the overall plot demonstrates excellent model performance. So looking at this plot side by side made our decision clear. While polynomial was good, the random for us just showed superior consistency and reliability in its predictions. This visual check gave us that extra confidence that random forest was the right choice to predict CLV accurately and reliably for the next step. Looking at the random forest future importance plot provides a clear insights into what drives CLV predictions. It's overwhelmingly dominated by two key usage metrics: frequency of SMS and seconds of use. Together, these accounted for over 95% of the model predictive focus. It clearly tells us that customer engagement through service usage is a primary driver of their lifetime value. Other features contributed only marginally, predicting the value amount. Therefore, based on its superior accuracy, which means high R square and low RMSE, stability shown in cross-validation, clear residual diagnostics, and clear interpretability, we selected random forest as our final model to generate the predicted CLV values. for use in our next stage, which is churn classification. Now, before we move to predicting churn, it's important to understand how we designed our experiment to test the role of predicted CLV we just generated. At the core of our hypothesis was whether this predicted CLV could be a practical and effective substitute for actual CLV, especially in the scenarios where real-time revenue might be unavailable. To test this rigorously, we set up a two-track experimental design. Track 1 was our proxy test. Here, we replaced actual CLV values with the predicted CLV values from our regression model and used these alongside other customer features in a logistic regression model to predict churn. The goal was to test performance. How will we predict churn when we substitute actual CLV with predicted CLV? This simulates those practical data constraints. Track 2 established our benchmark. In this track, we used the actual known CLV values from the dataset. We combined this true value information with all other features and used it to train more advanced classifiers: SVM, random forest, and XGBoost.
Now that we have predicted customer value, let's move to the second stage of a pipeline, churn classification. The goal here was simple: identify which customers are likely to leave the service and combine that with their estimated value so businesses can act strategically. We evaluated four models: logistic regression using actual and predicted CLV, support vector machines with linear, polynomial, and RBF kernels, random forest, and XGBoost, which excels on structured data. We use consistent features across models: customer behavior, seconds used, SMS frequency, account details such as status, plan type, and CLV, actual or predicted. Performance metrics included accuracy, recall, F1 score, and AUC, with AUC being key for separating churn from retained customers in imbalanced data. Let's zoom in on logistic regression to test predicted versus actual CLV. We trained two versions, one with actual CLV, another with predicted CLV from our regression phase, keeping other features identical. Results were solid. Actual CLV gave an AUC of 0.929, recall of 0.76, F1 score of 0.57. Predicted CLV edged slightly higher, AUC 0.929, recall 0.79, F1 score 0.59. This shows predicted CLV matches or beats actual CLV in simpler models, validating a pipeline when revenues data is missing. We ensured robustness with a stratified drain test split, smooth for imbalance, and AUC for reliable evaluation. Next, we benchmarked complex models using actual CLV. Logistic regression held steady, AUC 0.929. SVM with RBF kernel hit 0.956. Random forest reached 0.984, with a strong F1 score of 0.84. XGBoost topped it at AUC 0.985 with 0.95 accuracy, excelling at class separation, making it a top pick. This proves predicted CLV works for simpler models, while actual CLV maximizes complex model performance, setting strong benchmarks. Now let's take a closer look at a final model, XGBoost, which delivered the best performance across all metrics. First, let's look at the ROC curve. As you can see, the curve for XGBoost hugs the top left corner, showing excellent separation between churned and non-churned customers. The AUC score was 0.9845, which was the highest among all our classifiers. This tells us that the model is highly reliable at ranking customers by their churn risk, even in the presence of class imbalance. This strong ROC performance confirms that XGBoost not only fits well, but generalizes effectively. Next, let's take a look at what's driving the model: feature importance. Here's what we found. The most influential predictor was status 2, representing customers with inactive or suspended accounts, a strong signal of churn risk. The second most important feature was complaints, which is intuitive. Customers who have lodged complaints are far more likely to leave. Interestingly, customer value, our predicted CLV, also contributed to the model's decision making. This is important because it validates that a first stage regression output added real value to the second stage churn prediction. Other features like tariff plan and age group contributed moderately, possibly reflecting differences in churn behavior across customer segments. To summarize the stage, predicted CLV proved a solid stand in for actual revenue data, especially without full customer history. XGBoost led all models, hitting the highest AUC of 0.985 and strong F1 score of 0.84, making it a top classifier. Feature analysis showed churn driven by complaints, inactive status, and low engagement. Combining predicted value with behavioral and demographic features built an accurate, interpretable churn model. Next, we will explore interpretability with odds ratio and Sharpe values. Accuracy alone doesn't cut it for churn prediction. Businesses need to know why a model flags a customer. Interpretability builds trust, sharpens decisions, and ensures fairness. We use two tools, odds ratios for logistic regression and Sharpe for XGBoost. Odds ratios measure how features affect churn odds in logistic regression. A number above 1 raises churn risk, below 1 lowers it. Age group two's odd ratio of 6.87 showed those customers were nearly 7 times likelier to churn than the baseline. Customer value and tariff plan 2 with ratios below 1 reduced risk. For XGBoost, we used Sharpe, that is, Shapley additive explanations, which quantifies each feature's contribution to predictions, globally or per customer. Inactive status, that is status 2, was a top churn driver. High seconds of use, frequency of SMS, and customer value lowered risk. Sharp plots showed red dots for high, protective values, and blue dots for low, risky ones. Both approaches aligned. Complaints, call failures, and status changes spiked churn. Strong engagement and customer value kept customers loyal. This consistency between odds ratios, clear math, and Sharpe's deep dive into complex model gave us confidence. Our pipeline didn't just predict churn, it explained it, making insights actionable and trustworthy for business teams to craft targeted retention plans. Let's briefly connect these findings back to our exploratory data analysis. Our initial bivariate analysis revealed that a large proportion of customers with complaints had churned, and this has now been confirmed by both logistic regression and Sharpe. We also saw that customers with inactive status or lower usage had disproportionately higher churn rates. So, interpretability doesn't just validate our model, it ties back directly to real business behaviors. Let's now step back from the technical models and talk about the business takeaways from our analysis. Our two-stage pipeline combines predicted customer value with churn likelihood, empowering telecoms to focus retention efforts on high-value customers. This optimizes limited budgets for maximum impact, targeting those who matter most. We identified key churn signals. Customers with complaints or inactive status face the highest risk, while low usage, reduced SMS frequency, or call duration also flags potential churn. These aren't just numbers, they are actionable touch points. Businesses can offer high value, at risk customers tailored loyalty packages or discounts, route those with complaints to premium support for quick resolution, and re engage inactive users through usage based rewards or win back campaigns. By fusing machine learning with business logic, we transform reactive churn management into a proactive value driven strategy, making retention more effective and efficient.
As we wrap up, let's quickly recap what we accomplished through this project. First, we developed a two-stage machine learning framework that integrates customer lifetime value prediction with churn classification. This allowed us to go beyond standard churn models and focus on value-based retention. In the regression phase, we compared multiple models, including polynomial linear regression, decision trees, and random forest to predict CLV. We ultimately selected random forest for accuracy, stability, and strong interpretability. In the classification phase, we evaluated logistic regression, SVM, random forest, and XGBoost. XGBoost emerged as a top performer, achieving the highest AUC and strong FN score, particularly when using actual CLV. We also demonstrated that predicted CLV can serve as a reliable proxy, especially in scenarios where revenue data is missing, making our solution practical and scalable in real-world telecom environments. Looking ahead, there are several ways this pipeline can be executed. Apply the framework to larger, more diverse data set, evaluate predicted CLV with other classification models, explore more behavioral or engagement-based features, considering real-time use cases like monthly churn scoring.
This was a collaborative effort. Each of us contributed based on our strengths, ensuring that both the technical and analytic components were robust. We divided tasks thoughtfully and held regular sync-ups to maintain alignment across the pipeline. This helped us stay on track and deliver a cohesive and high-quality project. Thank you for watching our presentation. We have included our GitHub repository where you can explore the code and visuals used in this project. If you have any questions, we would be happy to answer through our emails.